Good afternoon. I'm Steve Thompson. I'm a researcher based at the Wellcome EPSRC Centre for Interventional and Surgical Sciences in London, UK. Here today to talk about our paper, Are Fiducial Registration Error and Target Registration Error Correlated? Using SciKit SurgeryFRED for teaching and research. So I'm afraid we're going to start with a bit of a spoiler. It's a very well-established fact that fiducial registration error and target registration error are not correlated. The paper title is a nod to a 2009 paper by Fitzpatrick, presented at SPIE, which basically says these things are not correlated and shows why. Yet, despite knowing this fact very well, it is commonplace amongst our students and also often clinical people who are using these systems to interpret a low fiducial registration error, basically a residual error, with a low target registration error. Target registration error is key to image-guided surgery. It tells you how close you are to your actual clinical target. You can't know target registration error for a clinical system, so you need estimators of it. Teaching this is a very important thing, obviously, clinically and for researchers in image-guided surgery. So in 2020, we were looking at ways we could do this teaching without being able to access the lab, so we need an online system. So we developed software, SciKit SurgeryFRED, which is what we've got today. FRED is the Fiducial Registration Educational Demonstration. I'll show you the software and share it with you today. So you can find FRED quite easily online with a simple search. We'll pull up the GitHub page. This is all open source software which you can contribute to, download, use for your own purposes. The prefix SciKit Surgery comes from our set of libraries that we've been developing, funded by Wellcome Trust and EPSRC, for surgical guidance system. They're small, compact libraries for surgical navigation. There's around about 20 of them. You can find them online at scikitsurgery.org, or you can just Google it. But the important thing with these libraries is we've set them up as being small and usable, but also production ready. They're fully unit tested, cross-platform. So we use them for our clinical applications that we take into theatre. And in the context of SciKit Surgery, FRED, what's important is that the algorithms that the program uses are the same tested, robust algorithms that we use for our clinical applications. So back to FRED, if you go on the GitHub page, there's a little Try FRED Here button, which will link you to an online implementation hosted on Google Cloud at the moment of the actual application. So what we have here is a preoperative image, an MRI scan, obviously of a brain, though in theory you can use any image you like. And on that image, we've placed randomly a target. This is basically a sphere. And each time you do a registration, it can be moved. We want to locate that target in the intraoperative image, which is the image on the right. All the surgeon can see in theatre is the exterior of the patient's head. This is all obviously a 2D plane for the purpose of running on a desktop computer, but it is, or the mathematics is completely 3D, so it's basically the same maths as we would use clinically. We can place fiducial markers on our simulated patient. And once we've placed at least 3 markers, we'll get an estimate of where the clinical target is. We can do that repeatedly. There's no limit to the number of fiducial markers you can use. Here, just do this. This is each time we place a fiducial marker, FRED adds a small but perceptible fiducial localization error. Here you can see crosshair is the actual known gold standard position of that fiducial, and the red dot is the position when it's being perturbed with an error. At the moment, we only implement errors in the intraoperative image. And we are told the statistics of the actual errors are shown in the boxes at the right of the screen. We can also see the target registration error manifested here. There's the difference between this crosshair center and the red dot. So you can get this up and you can use it as a teaching aid. You can get your students, you can ask them the question posed in the title of this paper, are these things correlated? And then you can set them off and get them to use Thread as a tool to explore this. And this is based on the idea of using divergent questioning strategies when you're teaching. And the idea is it should create a compelling demonstration that works better than just telling people these things are not correlated. You can also do fun things with Thread. Obviously, you can have a degenerate set of markers, fiducial markers. If you put all your fiducial markers up here, you'll get a nice low fiducial registration error and a rather nasty, massive target registration error. So you can demonstrate that quickly. And you can obviously get these things back by putting a more sensible fiducial pattern. We typically get the students to do about 200 registrations, which you can do in 10 minutes or so with this interface. And then you can plot the results. This particular result plot looks rather silly because we've only done 11 registrations, one of which was a deliberate mistake. But obviously, once you can see in the paper, once you get more registrations, you can get more sensible results. If you want to do tests of significance, there's a download button. You can download a CSV file and stick it in whatever your statistical analysis program of choice. So that works well. We've deployed this. It's a good teaching tool. It's flexible, enables you to cover a range of concepts very quickly, much more quickly than if you were doing pointers and stuff in the lab. You can realistically do hundreds of registrations. We've extended it to a game-based system as well. So you can click up here, play game. And that brings up much the same user interface, but we now have this dial down the bottom where we can do a simulated ablation. And we can place our fiducial markers in the same manner. And for the first couple of goes of the game, we're told the actual target registration error, which obviously is not a clinically feasible thing, but for training purposes, it teaches the students what they're aiming for. The point being here, if we know the actual target registration error, we know the margin. The margin, it would be equal to the TRE. So an actual TRE of 2.03, we need a margin of 2.1 to achieve full ablation. And then we get a nice positive score because we've treated the patient. However, if we do the next registration and set the margin smaller than the actual TRE, we'll get a negative score. So the game system then moves on to 8 more simulated ablations, telling the students a different statistic each time. So here they're being told the expected value of the FRE, which is a computational method, a way of working out what you expect the FRE to be. In this instance, I've done one earlier, got to the last registration. We're going to be told the expected value of the TRE, which is again a computation that Fitzpatrick came up with in 1998, I think, and underpins a lot of this research. So this isn't the actual TRE, this is the likely variance. So you can make a decision of your margin based on what you think is going to be safe, or if you're aiming for a big score, you can go a bit lower. We have a high score table, which is nice to hopefully motivate students to try and get up there and maximize their scores. The key point with the game from a research point of view is what we did is we recorded the results the students were getting and looked at how they varied depending on what statistic they were being shown. So consistently, if they're shown the actual TRE, they were getting higher scores than otherwise. But interestingly, for example, when they're only shown the fiducial localization error, they got lower scores. They tended to underestimate the error and undertreat the patient and get negative scores. We've only tested it on a cohort of 5 students so far, so we haven't got statistical significance. But what we're looking to do is test it on a much wider cohort, and as part of the motivation, moving the whole thing online so we can get people anywhere can use the system and play the game, and we'll be able to get a statistically significant look at whether telling the player a particular statistic has an impact on their clinical decision making, which then obviously would feed into research and using these systems in theatre. And we can extend it to more realistic models of fiducial localization error, things like anisotropic errors, like you'd see with an optical tracking system, or systematic errors where they're not purely independent. And we can also look at different registration algorithms, obviously, possibly surface-based registration, and visualization. So instead of just showing numbers in a box, we can show misaligned outlines of the outline of the skull and see whether that leads to a more intuitive understanding of the ablation margin, and whether it improves the simulated patient outcome, which is obviously what we're ultimately looking for, not the best registration, not the lowest TRE, but the best outcome for the patient. Obviously, in most cases, those things match. So that's SciKit SurgeryFRED. Thank you for listening. We are, as I said at the start, we are easily findable online. We're on GitHub. SciKit SurgeryFRED is deliberately chosen as an easily searchable term. So have a look, contribute any questions, raise issues, bug reports. Have a go at using the online implementation, which is you can find on the GitHub page. Brilliant. Thank you.